Okay, let's get started. Hello, everyone. Welcome to the Space Science Seminar Series hosted by the Center for Space Science at NYU Abu Dhabi in collaboration with the UAE Space Agency. Today's speaker is Dr. Konstantin Herbst. He got his PhD from the University of Kiel in Germany. Then he did a postdoc there, then did another postdoc at Lund University in Sweden. Then he moved back at Kiel as a research associate and as a lecturer, and he's been over there since. He's an expert in several areas of space weather physics, both solar and stellar space weather. He works both on extrasolar planets as well as on solar system planets, so Venus and Mars. And so, Konstantin, welcome, and please get started whenever you're ready.
Thank you for the nice introduction, and thanks again to the organizers for organizing the conference and for giving me the opportunity to speak a bit about our newly developed model suite to determine the influence of cosmic rays on planetary chemistry and atmospheric biosignatures. Now, to come up with such a model suite as I will present it is a team effort. So I have to thank also my collaborators, especially the group from Heike Rauer at the DLR and TU Berlin, as well as the Karlsruhe Institute of Technology with the lead of Miriam Sinnhuber. And I also want to highlight our former and still PhD students, Markus Scheucher, Vanessa Schmidt, and Sascha Baniatz, who were funded by the German Research Foundation on a project where we developed this model suite. Now, I'm from an exoplanetary background, so I start with the obvious. So our sun is a star, and our sun has planets. So it's fair to assume that stars outside also have planets. And we know that this is true since 1995. When Hubble detected its first hot Jupiter. So over the past 2 decades, as shown here, a multitude of dedicated missions, like, for example, Kepler, the Kepler mission, as Jutta mentioned last week, or TESS, or Gaia, whatever you want to name, searched particularly for exoplanets outside our solar system. And as of today, and I checked this morning, we are talking about 4,179 exoplanets in 3,109 planetary systems, of which a dozen, so around about 10 to 12 planets, are assumed to be within the habitable zone of their star. And habitable zone meaning the zone around the star where the conditions are not too cold and not too hot, so just right in order to sustain liquid water on the surface of the planet. And since we know that water is the key ingredient for life as we know it on Earth, we might have the chance to find life outside our solar system in the next decades. Now, in the search for planets and in the near future, in particular Earth-like planets, we are able to address some of the most amazing and mysterious questions that humankind has faced for centuries. So the basic question is there life out there? And if there is, who is out there? So basically we are asking, are ETs flying around? And for those who don't know it, this is the extraterrestrials, so the ET group from the University of Kiel, where I'm located at. Now, to study planetary habitability, detailed knowledge on the astroperiodic particle and radiation environment needs to be known. We need to know about the interaction of this radiation and particle field with the planetary magnetic field, as well as atmosphere. And in particular, we need to know about the atmospheric ionization, the climate, and the chemistry of the planetary atmosphere. Now, the goal of one of the goals of our model suite is to understand the observable biosignatures, so signs for life on other planets, which will be measured, for example, by the James Webb Space Telescope. And if everything goes well, James Webb will be launched next year. So within the next years, we hope to find signs for life outside our solar system. And these biosignatures, just to give a heads up, are biosignatures like ozone or methane, which are biotically or abiotically produced in the atmosphere. Now, this is a newly emerging field and still fast going with exoplanetary research. Please feel free to have a look there. So this is the outline of my talk, and we will start with the necessary background, and I will tell you something about planetary climate chemistry modeling before we come to our self-consistent simulation chain and its validation against modern Earth, because we have to go back to the solar system because here we have the necessary measurements to compare our model results with. I will give an insight in an exoplanetary Earth-like planet around Proxima Centauri b, Proxima Centauri b, and I will also show you our first results on modern Mars, which are still preliminary because we started a few weeks ago. Now the background, let's start by looking at what we know about the sun, and in particular the particle environment, the planetary magnetic fields, the atmospheres, and the interaction of particles within those. And I'm pretty sure for those of you who followed the first talk by Guillaume know about this. So we are focusing on two populations of particles, so galactic cosmic rays, which are shown here in green. So you see the energy distribution, or the differential particle intensity of protons. So green are galactic cosmic rays, so particles originating outside from our solar system. And you see in red these solar energetic particles. And you heard last week that there are strong events or strong accelerated particles, which are known as ground level enhancements because they can be measured at the surface of not only the Earth, but also Mars or the Moon, for example. Now, what you also see is that galactic cosmic rays are modulated, and this has to do with the solar magnetic field. So the sun has a magnetic field, it has a solar wind, the magnetic field is frozen in the solar wind, so the magnetic field is carried outwards, forming the heliospheric magnetic field. And because you have also a local interstellar medium, which is streaming onto the plasma bubble, so to speak, you have the formation of heliopause, determination shock, or as well bow shock. Now you can model these quantities inside, for example, particle densities or the distribution of the magnetic field in an heliosphere or an astrosphere with the help of ideal 3D MHD equations, and for example with the Kronos code, which I don't want to go into detail. However, what I want to highlight is that we used this model most recently for the first time to model the diversity of M-star astrospheres. So whoever is interested in that, please feel free to have a look there. So you can model the astroperic or heliospheric conditions. And what you then can see is that there is a presence of a solar cycle. So we have a solar minimum and maximum conditions, which are changing every 11 years, as you can see by ground-based measurements here shown for the neutron monitors of ULU. So you see during solar minimum conditions, you have a maximum in the count rate, and during solar maximum conditions, you have a minimum in the count rates you can measure at the surface of the Earth. What you also see is these 11-year periodicity. However, there's also a 22-year cycle, which is due to the magnetic field reversal. So every 22 years, you get the original configuration. And you have a flattened followed by a peaked structure, and then a flattened and peaked again. So it's distinctive cycles, which have, and these flattened and peaked structures have to do with the particle transport inside the heliosphere. And what you also can see from this movie here is this, that due to this changing activity, you get a pulsation of the heliosphere due to the activity changes. And shown here on the right-hand side is a study by Berger et al. 2020, which should show you that this variation is not only visible at Earth, but also at Mars, shown here in red, and the Moon, shown in black. So we see this modulation due to the heliospheric activity. Now, the transport of galactic cosmic rays within this heliosphere depends on the volume, of course. It depends on the structure and the level of turbulence inside the heliosphere, and it can be described by Parker's transport equation, where you have diffusion effects, we have the convection and drift effects of the particles we have to take into account, as well as adiabatic changes or additional sources like, for example, the Jovian electrons. There are two ways to solve this. Either you solve it analytically, which a lot of people are doing by using, for example, the force field approximation. Well, this reduces the Fokker-Planck-like equation to a simple parameter, the solar modulation parameter, which is good and bad because you have to neglect important physical principles like drift effects. And you can also use numerical solution methods like, for example, the stochastic differential equations, where you can use the output, for example, of your 3D MHD model as input for the stochastic differential equations to get a more reliable view on the modulation of particles. So if we compare the analytic solution here shown as a solid line and the numerical solution shown by the red line here to Pamela measurements, so you see the differential intensity of protons measured by Pamela versus the kinetic energy of the particles, you see that both methods work fairly well. Actually good for the stochastic diffusion equations and fairly well for the analytic solution. And this is a known problem and has been addressed most recently. And this has, to tell you the truth, it has to do with the neglect of the drifts inside the heliosphere. Now, when it comes to solar energetic particles, you have to take the transport focus transport equation, for example, by Roloff. So you have streaming along magnetic field lines, so along the heliospheric magnetic field. You have focusing effects as well as pitch angle scattering you have to take into account. So basically a planet which is close to the heliospheric magnetic field line, like point C here, will encounter an enhanced solar particle flux, which may be detected then on the planetary surface. So if this was Earth or Mars, there would be an increase in the particle flux. The problem with this method is that you need information on the injection profile, which is, you have an idea when it comes to the sun, but when it comes to other stars, you have no idea, and you need to use an approximation or a relation known from the sun in order to get your particle spectra around other stars. And there is this one correlation known as the peak size distribution function, which is a power law relation between the flare intensity and the accelerated particle intensity, which can be used to get your spectrum. Now, Jutta already told last week that sun-like stars are producing really strong energetic particle events once every up to 1,000 years. And actually there are indicators detected at Earth in the so-called cosmogenic radionuclide records, which are naturally stored in, so cosmic rays are, cosmogenic radionuclides are naturally stored in trees or in sediments or ice sheets, where you can extract the information. You see these increases, for example, around 774, 775. So there are indicators that the sun produced extreme events, and there is a newly selected ISI team by Fusa-Miyake and Ilya Soskin, which will study these extreme events and their impact. So there will be new studies coming along. Now, the heliospheric magnetic field is not the only magnetic filter for low energetic particles. We also have to address magnetic fields, planetary magnetic fields. And as you can see, not all planetary magnetic fields are alike. So shown here is, for example, the Earth with an internal magnetic field, dipole-like, and an external magnetic field. We have also the Venusian magnetic field, which is induced by the solar wind. So the solar wind is interacting with the upper Venusian layers by inducing this magnetospheric field. And as you can see here, shaded in brown, this is the size of the Venusian magnetosphere compared to the Earth's magnetic field. So it's much smaller than what we have at Earth. And what you also can find are crustal magnetic fields, which, like in the case of Mars, there has been a magnetic field which got lost somehow, and you have the information stored in the sediments and the rocks on Mars. Nevertheless, energetic particles that enter the atmosphere lose their energy most likely due to collisions which lead to atmospheric ionization. You have dissociative ionization, excitation, and dissociation of most abundant species in the upper layers. Now, the further down the particle is able to penetrate into the atmosphere, the more likely an interaction with atmospheric constituents like nitrogen, oxygen, and argon become. So by interacting with them, you generate the production of secondary particle cascades. So you have an electromagnetic branch, you have a muonic branch, you have a hadronic branch, which then, of course, further lead to the ionization of the lower atmosphere, but also to changes in the atmospheric chemistry due to the electrons which are produced in these secondary particle cascades. So you have photochemical effects, and these electrons here in particular created in the secondary particle showers may lead also to the breakup of molecular nitrogen and oxygen, followed by ion and gas phase chemistry that produces nitrogen and oxygen oxides. And these in turn, then of course, can catalytically remove atmospheric ozone, which we will hear about in this talk a bit more, and therefore lead to an enhancement of the harmful UV radiation on the surface of a planet. Oh, sorry. Now, speaking about chemistry, we have to take care of planetary climate chemistry modeling. So this sketch shows the ion-related chemical processes induced by the sun, by galactic cosmic rays and solar energetic particles. And the energetic particles, as I told you, precipitating into the atmosphere lead to changes and ionization and stuff like that. So this greatly, of course, disturbs the chemical composition from the lower thermosphere down to the stratosphere. Now, most important are changes due to, or to the budget of the atmospheric nitrogen oxides, so NOx, so NO, N or NO2, as shown here, as well as the atmospheric reactive hydrogen oxide, so HOx, which both contribute then to the ozone loss in the stratosphere and mesosphere. And in NO2 dominated atmospheres, so Earth-like atmospheres, this leads to the production of, for example, excited atomic states or ions like N2 plus or O2 plus, and in CO2 dominated atmospheres like Mars and Venus, ions and excited state dissociation products of CO2 would likely be the primary product. Now, atmospheric ionization further leads to chains of very fast ion chemistry reactions, which in Earth-like atmospheres lead to the formation of neutral reactive radicals like NOH and OH, which then contribute to the catalytic reaction chain, which, as shown here as an example, leads to destroying of ozone in the atmosphere, which is also shown here in from actual measurements with the MIPAS instrument. So we see ozone changes over the course of time, induced by two distinct events, which are known as the Halloween events. So you see with the incoming energetic particle event, you have ozone losses throughout the almost entire atmosphere, which take days to recover from when it comes to ozone changes. Now, since ozone is the main contributor for radioactive heating in the stratosphere, this directly affects the atmospheric temperature and circulation. So in order to take all of this into account, so all the ionization rates, the secondary particles, the chemistry climate interactions, we built our new self-consistent simulation chain. And as you see down here, and because it's a team effort, we coupled three models in order to achieve, to get information about the habitability of exoplanets. So we will start with the one developed in Kiel by our former PhD student, Sasha Banyets, which is the atmospheric radiation interaction simulator. And I will not go into too much detail here, so please feel free to have a look at our paper. Now, ATRIS was developed to study a variety of planetary atmospheres. So it's a newly developed GN4-based code, which specifically enables the parametric studies of radiation propagation through various exoplanetary atmospheres. And one of the main purposes is the calculation of ion pair production rates, which are mandatory input parameters for all chemistry climate models. So ATRIS has been validated extensively over the last year. So we have two papers focusing on Earth, as shown here, both by Sasha, where you can see a good correlation between the ion pair production rates, depending on the altitude inside the Earth's atmosphere, compared to measurements, for example, by Near et al. We also find a good correlation between the secondary neutron flux measured here in black and modeled in blue, but also a good agreement between the modeled absorbed dose rate here in purple and the measurements with the FRED instrument, which also is an instrument developed which has been developed in our group by Thomas Müller in 2013. Now, we also have a paper focusing on deep space missions, so Moon in particular. And we have two papers, as Dimitra mentioned already, focusing on Venus and the effect of cosmic rays in particular, or in the context of habitability, both published in A&A. And we also have two papers studying or showing studies on Mars, which I will show in the last slide of my talk. Now, we have these ionization rates, and we have two chemistry models, one chemistry climate and one ion chemistry model, which need to use, or which have to use, our ionization profiles in order to go forward. Now, I'm not an expert in both codes, so I would just tell you the basics about these codes and refer you to the papers which are currently in prep or have been published already. So we have the 1D TÜV model, which is from the Technical University of Berlin, which dates back to Casting et al. 84, sorry. And as you can see, it has been updated quite a lot over the years. And it's a steady state 1D cloud-free radiative convective module to calculate the atmospheric temperature and water content. So we have a climate part, which now has been updated to Red Fox, and a chemistry part, which has been updated to Black Wolf, as you will see in the next slide, calculating the steady state mixing ratios of 128 species of 1,127 reactions. Now, I will skip the details. What you need to know is that prior to our simulation chain, people often use the approach by Geisler-Hillers to come up with the ionization rates in the atmosphere to be put in chemistry models. And now with ATRIS and an interface between both codes, we are able to directly process the input from ATRIS in this 1D TUP model. However, what is missing in the code is the ion chemistry, and there Miriam's group comes into play because they developed an ion chemistry code called Exotic, which we discussed here. Exotic is an update of the University of Bremen ion chemistry model, UBIC. So see Zinhuber et al. 2012 for a detailed study. And well, in general, we have 60 neutrals, 120 charged species, about 600 neutral ion recombination, and so on reactions. And just to give you an idea, so my head is always blown up when I look at this. So shown here is the negative ion chemistry in Earth's atmosphere for electrons, and they are taken into negative ion cluster ions, which are shown here in white, and then are released, or they release quantities like CIO or HNO3. So please feel free to look at the validation studies in the literature. Now, I told you we have a code for the ionization rates and the dose rates. We have a code for the climate chemistry modeling, and we have a code for the ion chemistry modeling, and coupling all of those in a model chain will give us a quite massive or quite strong tool to investigate exoplanetary habitability. Shown here is our model chain, so to speak. So we start with the spectrum of the star. We need to take into account UV fluxes, which both chemical models need as an input. We also need to address the cosmic ray spectrum for galactic cosmic rays, as well as solar cosmic rays. We need to address the magnetic field, which is done in our model suite by Planetary, which has been developed by Laurent Desorger at the University of Bern in Switzerland, in order to provide top of the atmosphere fluxes. Now, with these top of the atmosphere fluxes, we then can directly derive atmospheric models. In order to combine ATRIS with the 1D TUP model, we take composition and temperature profiles from the 1D TUP model, and then model the ionization rates, which go directly in both codes. With this information, we have composition and temperature profiles again, as well as the ion chemistry. And therefore, because we have to couple these codes with each other, we have two iteration stages, first between the ion chemistry and the atmospheric chemistry and transport model. And we have another one between ATRIS and the 1D TUP model when it comes to composition, because as you will see later on, the cosmic rays induced in the atmosphere change the composition and the ionization profiles. And with that, of course, we can get direct outputs like, for example, the dose rates. We can have the direct information about the UVB and UVC flux, as well as use analysis tools like the garlic code from Franz Schreier from DLR to get information about the transmission spectra, as well as the PUP tool from Lehmann et al. From the TU Berlin in order to get information about the chemical analysis in altitude profiles. Okay, so we have our new simulation chain. We have our codes. We have we came up with this model interaction tool. Now let's have a look at the first validation study on modern Earth. So what we need, sorry, it's a bit small. What we need is, of course, a spectrum. So we decided to go with two scenarios. First of all, with a galactic cosmic ray background spectrum, and then with one of the strongest ground level enhancement events on Earth, the GLE-05 from February 1956. Now, I told you about the iteration phases. So we noticed that for the case of galactic cosmic rays, you only need one iteration. So you do all the modeling one time and nothing changes inside the atmosphere. So the temperature stays the same, the ion chemistry stays the same. So for galactic cosmic rays, you only need to run the model or the model chain once. However, in the case of strong energetic particle events like the GLE-05, we found, at least for this one, that we need 3 iteration runs in order to have a diverge or a fixed atmospheric response. So just keep in mind that energetic particles from the sun lead to various changes in the atmosphere, and that we have to iterate it more than once in order to get the full picture. Now the full picture is shown here in the lower part. So we have the ion pair production rates in the left panel for the GCR case and the solar energetic particles. And as you can see, compared with each other, an increase of the ion pair production rates of about 2 orders of magnitudes in the maximum here can be found. And this, of course, translates directly to the ion chemistry shown here. Now, with this information, we can address 3 science questions. First of all, how do cosmic rays and the resulting photochemistry affect the abundance of potential biosignatures? And I told you about the destruction of ozone in the atmosphere. So shown here is the ozone loss pattern for the galactic cosmic ray case and the case of the GLE-05, analyzed with PUP by Lehmann et al., which directly uses the output from the 1D TUB model. So illustrated is the well-studied ozone UV feedback, which is a self-healing mechanism, which helps to maintain the ozone layer. And as you can see, the peak loss rates for ozone, so the peak here and here, increases by about 15% when the GLE is induced into the atmosphere. And additionally, you see that the altitude of the maximum is going down about, I would say, 3 to 4 kilometers in case of the GLE event. Now, the other question you can ask yourself is, what is the radiation dose at the surface and how strong is the surface UV radiation exposure, which is shown here. So we have in the upper panel the altitude-dependent absorbed dose for both scenarios of GCR and GLE event, and the dose equivalent, which is more reflecting the impact on human tissue. And on the lower panel, you see the changes of the UVA, B, and C flux, so the cosmic ray-induced chemical changes in the atmosphere. And as you can see, neither UVA nor UVC change dramatically due to the impact of the GLE event. However, the UVB environment shows a clear increase in the lower atmosphere. And in an Earth-like atmosphere, the main absorber in the UVB ranges is O3. So our biosignature ozone is highly responsible for these changes here. So the enhanced UVB flux shown here corresponds well with the reduction of the O3, so the ozone, by up to 50% in the flaring case. Now shown here, the third question you can ask yourself is, how do cosmic rays affect the spectral features of biosignatures, which is shown here. So reflecting a potential James Webb Space Telescope measurement of an Earth-like planet around a G2 type star, like our Earth. And you can see distinctive features here. You can see the ray light extinction slope in the UV visible. You can see the rotational vibrational water and methane band in the near infrared right here. And what you also can see are characteristic features like the ozone and the CO2 here and here. And what you also can clearly see is that ozone is reduced to the GLE, as we discussed before. However, there is this feature in nitric acid, HNO3, which is really enhanced in case of the GLE event. Now, this has also been found prior to our study in Earth-like atmospheres around M stars by, I hope I can pronounce this correctly, Tabata Wakili et al. 2016, which proposed such a feature as a measure for the activity of stars in Earth-like atmospheres. So our study is validating or strengthen their argumentation. Speaking of M stars, I wanted to show you our application, which most recently was published in APJ on M star, so Proxima Centauri, our nearest neighbor, which is only 4 light years away, and its planet Proxima Centauri b, which most likely is Earth-like. So I told you, or Yuta also told you, that other stars are much more active than our sun. So we have a much higher particle flux we have to address when it comes to stellar particle environment. And of course, with that, you have a much higher ion pair production rate in the atmosphere, which can vary depending on the method you use in order to derive your spectrum. And what I want to highlight is the possible transmission spectrum of Proxima Centauri b right here. Also, again, showing that this feature of HNO3 is really enhanced. So, concluding, this biosignature could potentially be used as an indirect hint for the presence of HO2 in the atmosphere. And also you can see that the O3 feature is really suppressed, as well as the methane feature is going down. So these two biosignatures might not be the best ones to study for future exoplanetary investigations or in exoplanetary investigations. Okay, so thank you for your attention, and I'm open for questions.
Thank you, Konstantin. Yeah, interesting talk. A lot of topics to cover, starting from the stars all the way to planets and chemistry.
Yeah, that's the problem. You have to take a lot of information into account in order to get the information as best as possible. So I know it is a lot.
Right. Yeah, so what are you doing with the Martian chemistry part? Are you using any code to do that? Are you building your own code? How are you doing that?
We updated our own code. So the 1D TUP has been updated. The exotic code has been updated for CO2 dominated atmospheres. So yes, and we also want to tackle the Venusian atmosphere, a thick CO2 dominated atmosphere, but we can also, or we want also to study the atmosphere of Titan, for example.
Right.
So these are ongoing projects, and we saw that the market is open for studies like this, so we try to tackle as much as we can right now.
Yeah, yeah. NASA has funded 2 Venus missions
Yes,
recently.
I
So,
know.
yeah.
Yeah.
Uh, there is such an extraordinary amount of detail in these models. I'm amazed how many reactions you have and things like that. But with respect to the impact on the Earth, could you compare the effect to something more familiar? I don't know what that might be, just so you have some feel for how important it is.
Well, we studied or we investigated the models and compared it to, for example, the MIPAS instrument. So there is a long history of validating both codes. So for Earth, so in an N2O2 dominated atmosphere, this works fantastic. So, and for, for CO2 dominated atmospheres, we don't have any point to validate because there are no measurements yet.
Okay.
So we will have to wait for future studies and measurements and instrumentations. Right?
How big are the impacts on, say, O2? It wasn't clear to me. Yeah.
Yeah, I'm not the expert on this. I have to tell you the truth right away. So me and chemistry is I'm trying to wrap my head around it, but I can't go into detail. So maybe Dimitra can be of help if possible.
Yeah, the flux is more than twice lower on Mars compared to the Earth. So the size of the effect is much smaller. And the Martian atmosphere also responds much quicker to
Right.
all these events compared
Yes.
to the Earth.
Right. Okay.
Yeah, so please use the Q&A feature. We have a question from Rasha Al-Shehi, and she is asking, what is the source of your data?
Sorry, the source of my data?
Yeah.
Which data? I don't know which data. So well, for Earth, we have the ion pair production rates measured in balloon flights with certain instruments taking care. We have the radiation, those can be measured with certain detectors which are flying. For example, the Dostal instrument on board the ISS. We have instruments which are flying at flight altitudes in airplanes. We have the radiation detector on the surface of Mars. So we have, speaking about the ion pair production rate or the induced radiation doses, we have instruments on board certain missions which can give us answers to this question. We also have crater measurements for the moon, and so we are fine there, I think.
If you go back to your earlier slides, I think maybe the question is about one of those slides.
Which slide?
Number 3 or 4 or something like that.
3 or 4? Okay.
Yeah.
3 or 4. Well, these are, yeah, I think.
This one, let's say, maybe the question relates to this.
Okay, so we have the Pamela instrument, for example, or we have AMS, which measure the galactic cosmic ray flux for a few years now. So we see this modulation right here. We can actually see in the measurements of, for example, Pamela, that the problem is that these data are not, it's hard to get the data. And there are only a few publications which deal with the subject right here. And yeah, well, the GLE events, for example, are also measured with the GO satellite, for example. So you have a particle detector on board of your missions in space, and they can measure the energetic particle flux, and so you can derive such differential fluxes like this.
This is almost like a -2 power, isn't that right?
Yeah, that's right. So it's a rather steep spectrum.
Yeah.
But, you know, just because there are not many doesn't mean that they don't have impact on planetary atmospheres, because we saw this in a study for Venus. So most of the people stopped at 1 TeV energies of galactic cosmic rays. And we can show that in case of the Venusian atmosphere, which is a much thicker atmosphere than Mars and Earth as well, you have to go up to 10 TeV in order to get the full spectrum. So it doesn't mean only because there are few there that they don't have any impact on the magnetic, or to speak, the atmospheric interactions.
Yeah, especially in case of Venus, if you
Yeah.
go at greater depths, then most of the low energy particles won't even reach there. So
Yeah.
Yeah, I mean, what is the level of energy that will reach the Earth, for instance, here? What level of energy should we be concerned
Do you
about?
mean the surface, or?
Yeah,
Well,
surface.
it showed that, or well, I can only speak about studies I did in my PhD times. So I think between 100 GeV and 1 TeV, there is not much change. So basically, I don't know if this still is the case, but most people model up to 100 GeV and then they stop.
Okay.
Because the impact is neglectable.
Okay. Okay. You can simplify the number of reactions you have in your model, right? You have so many of them, so you must have some reduced models that probably work as well.
I'm pretty sure they have.
Mm.
Yeah. But then again, you can, there is this, wait, let me go to the slides. So there are these two new papers. So I know that Fabian's paper is in press now, but there is this new update paper from Marcus. So you can read all about it in there. So the information is there, and they are happy to answer your questions. So in case anyone is interested, please feel free to contact them. They are more than happy to, share their knowledge and help other people, or even, get information themselves, of course.
There are other questions here, so.
yeah, Konstantin, can you see the Q&A feature?
No, I can't.
Okay, so I'm going to ask one question, which is by Mohammed, and he's asking, how does an instrument differentiate between solar and cosmic radiation?
Well, this is a good question. Well, the particle instruments usually are built for a specific energy range they should focus on. So there are, I'm way out of my comfort zone here. So there are, anti-coincidences and stuff like that to get rid of the particles you don't want to see in your detector, I assume. So, and in case of, for example, the Dostal instrument, where you fly through the South Atlantic anomaly, where you have high particle increases, you don't distinguish. You can see it from the spectrum where the South Atlantic anomaly is located. So you have to, use your spectra and then work with them and have a look at what you know about the physics behind it. Yeah.
We have somebody's raising a hand. Hi, Said. Please ask a question.
Hi,
Hi,
how are you?
I'm fine, thank you. How are you?
Can you go ahead and ask a question, please?
I assume there was no question.
Yeah, okay, because it was.
There is something here. About the observatories on Earth to assess cosmic rays.
Yeah, so there's a question about are there any observatories on Earth to assess cosmic rays?
Yeah, so there are neutron monitors, which are distributed all over the globe. So we have a network of neutron monitors and also some mini neutron monitors, which are on board of ships going north and south, where you can detect galactic cosmic rays as well, or the impact of galactic cosmic rays to the atmosphere. You can see ground level enhancements. You can see that galactic cosmic rays are isotropically coming in, so from all sides distributed the same, while GLE events are anisotropic. So you have, in case of a GLE event, you have neutron monitors which respond to the impact by increased count rates, and some of them see the event and some don't. So you can have information about the asymmetry of the event as well. And then you have, of course, cosmogenic radionuclides. However, they cannot be used for the modern era. They are more can be seen as a mirror to the past of the sun. So you can see there these ground level enhancement or potential ground level enhancements throughout the time of the sun, or let's say about the last, I think it's 10,000 years where you have accurate measurements from. And you can find that the sun had grand solar minima, so times where over hundreds of years the sun was basically inactive. But you can also find times where the sun was highly active, so grand solar maxima as well. So there are these natural cosmic ray detectors and the neutron monitors as current cosmic ray detectors. And there's also studies going on, and this might sound a bit far-fetched, but we are working together with people from the hydrology department. They are measuring water content, and what they also measure is surface neutrons. And well, we find a correlation between what is going on in the terms of hydrology and the cosmic rays. So there is this new DFG project going on right now to investigate this as well. So there might even be more cosmic ray detectors than we, so far have thought about.
Interesting.
There is so much work going on in artificial intelligence and machine learning. Do you see any important use to which those studies can be put in terms of understanding cosmic rays and the analysis of the data?
Well, there are already attempts to do this. I know that they are trying to, I don't know which group it is, but they are trying to use AI for, how is it called? I said it before, for forecasting the induced responses of the atmosphere. So there are already people who are trying to use these methods for the cosmic ray community. And it's also for so a lot of people are trying to use these new methods to get a better feeling or to test the methods. Well,
I think there may be another question, not sure.
I see some Q&A and I can't open it, so I'm sorry I can't have a look at it myself.
Yeah, so there is a question where they're asking, do orbiters and other space satellites need shielding from cosmic rays?
Well, the satellites, well, you have these effects of induced currents. So to some degree, you have to shield your spacecraft, but I think, well, this is a topic, but more importantly, you have to shield your crewed space ship. So if you want to fly people to the Mars or Moon or wherever, you have to take care of the people more than the instruments, I think. So I think with the detectors on board of satellites and stuff, we have a long history and we know what we are doing. But in case of sending people to other planets, I think we have to do more studies in order to assure that they reach the planet safe and sound, or the moon safe and sound.
And come back.
And come back. Well, this would be a great thing.
Maybe they don't want to come back.
Yeah. All right. If there are no more questions, let us thank the speaker. Thank you, Konstantin, for your talk. And yeah, thanks everybody. See you all next week.
Okay. Bye-bye.
Okay, bye. Thanks, Konstantin. Bye.
Bye.